Hey everyone, welcome to the first lecture of the second module of the DSA course. So in this lecture, we will be discussing about stacks. Okay, before starting with the stacks, I need to discuss the basic classification of data structures that we have. So generally, data structures are classified in two categories. The first one is primitive data structure, and the second one is non-primitive data structure. So this primitive data structure we already know, and these are also known as data types. Yes, it is same as the data types that we discuss in any programming language. Okay, so we have say int, float, and so on, character, string. So these are the basic building blocks of a programming language. All right. And second, we have this non-primitive data structures. And this non-primitive data structure is further classified as linear and non-linear data structures. And as the name suggests, the linear data structures are generally stored sequentially in the memory. So in this linear data structure, we will study arrays, stack, queues, linked list. That's it. And in non-linear data structure, which are stored in non-sequential manner, or you can also say that these data structures, the data is stored in a hierarchical manner. So generally, trees and graphs lie in this non-linear data structure of non-primitive type. Okay, so since these data types and array is already discussed in the programming course, so we won't be discussing it over here. So this module specifically will be discussing these data structures: stacks, queues, linked list, and one more, hash map. Since hash map is not like in this linear data structure category, but we will be discussing hash maps in this module. Okay, so let's get started with stacks. So what exactly a stack is? So like, since we already know that data structure is basically a way in which we store data so that we can use it in an efficient manner. Okay, so here first in the list is stack. Okay, so stack is a linear data structure which is the data is stored sequentially, which follows this property called LIFO, or you can also say which follows this principle LIFO, which stands for last in, first out. So a simple analogy, you can see there is an image given in which we have a pole, in fact a fixed pole. We have a fixed pole and a rod is fixed with this pole. Okay, so we have this rod, and then we have this circular weights which are inserted in such a way that you can only insert it from this direction, and the other end is already fixed. This end is already fixed. So let's call it this as weight 1, the middle one is weight 2, and the black one, which is the last one, is weight 3. Okay, so there is only one way in which you can insert these circular weights in this rod, which is W1 first, then W2, then W3. So if I have to ask you a question, is there a way that you can directly pull out W1, which you have inserted first, directly without moving this W2 and W3? No, right? Since it's the other end is already fixed, there is only one way in which the weights can be inserted and pulled out from this cylindrical rod, and this is of last in, first out fashion. The weight which is put in that rod last will be the first one to be pulled out. Okay, last in, first out. So the order in which you can take out these weights will be W1, W3 first, then W2, then W1. There is only one way possible. So these sort of data structures in which LIFO is the only possibility are known as stacks. Okay, so like it's a classic example, you must have seen it in all these gyms and training centers. So this is the array representation of this stack. Okay, so we have this array of sequential memory in which the pole can be assumed over here, which is fixed. You can only put elements from right hand side, and you can only pull out the elements or the integers from right hand side of this array. So first element to insert is, let's suppose 15. You have inserted it first. Okay, then you have inserted 6. Then you have to insert 2. So 2 will be on top of 6, not on top of 15. Okay, and finally 9. So there are 4 elements in this array, which is in fact a form of a stack. Okay, so if you have to pull out an element from this array, which is a stack, the only element that can be pulled out, this has 4 elements, right? But the only element that can be pulled out is 9. Why? Because it holds the property last in, first out. So the element which you have put in this stack, the latest one, will be the first to be pulled out. Then only this data structure will be called as stack. Otherwise it won't hold the property of the stack. Alright, so here's the key analogy. You can stack plates or books or plates in such manner, or you can also stack books in a shelf and so on. So like there are various examples and analogies we can have in our day-to-day life for the stack data structure. Okay, so one more important thing. So there is a parameter associated with these stacks which is called as top. What exactly it is? So this top, it's the index of the top element in that stack. So there will be multiple elements in that stack, right? So the index of the topmost element, the value of that index is known as, will be equal to the value of the top. In this case, if the array index is starting with 1, then s dot top will be 4. The element number 9 at index 4 is the topmost element. So s dot top is not the value of the element, it's the index. It's the index and the value is 9. Okay, why we have to maintain this top? Because like we will be using this top in order to identify that what is the position of the last element which we have added to this stack, so that any deletion operation can be not exactly only deletion, all deletion will be occurred from top and addition will also be occurred on this top. How exactly? We'll see it in some time, but this is the parameter that is usually associated and we usually store it when we talk about the stack data structure. Okay. Next is, let's discuss the operations, the various operations that we can perform on this data structure. So the first in the list is push operation. It is also called as insertion. So the insertion operation to add a specific element in that stack is denoted as push, and we pass two parameters s and x, where s is the stack himself and x is the element. X is the element which we will be putting or inserting on the top of stack. You can only put elements on the top. That's why the importance of this index top. Okay, so here's the pseudocode. It will be like this. There will be some elements already present in the stack. Let's take this example only: 15, 6, 2 and 9. 15, 2, 6 and 9, and the index is starting with In this case, 1, 2, 3 and 4. This is the index and it's the value. Okay. So I need to insert the element on the top of the stack, and s.top, I already know that s.top is 4. Why? Because it is the index of the topmost element present in this stack. So if I have to push a specific element in this stack, so what will be the position of the new element on top of it, right? So it will be 5. The new element that I need to insert will be at 5th index. Okay. So here it is. If I have to push x in this s, so first I need to increment the value of top. I need to increment the value of top by 1, and this top plus 1 will give me the index at which x can be added or put. Then this s dot top will be equal to x. Okay, we have initialized this. This will be top plus 1. This index is s dot top plus 1, which will be 5. Right? We have incremented top with s dot top plus 1 and then added s of s dot top will be x. So element x will be inserted at the 5th index. Okay. So here, like, one important thing got missed, like not got missed, I didn't added it over here, which is the overflow condition. So since many programming language allows us to initialize these arrays in a fixed manner. Okay. So what if you have initialized this array with size 10? Okay. So in that case, while inserting, first we need to check for overflows. So always check for overflows. What exactly an overflow is? Overflow is a state in which the array is like completely full and there is no space to add an extra element in that array. Okay. So overflow is when the array is full or the stack is full. Stack is full. And how exactly you can check? We can check, say, what if the size of, like, I am assuming that we are like starting with index 1. In that case, s dot top, if this is equal to size of stack, let's assume the size is 10. So s dot top will be, if the stack is entirely full, the value of s dot top, which is the topmost element in that stack, its index will be 10, right? And 10 is the size of stack. So this will be the overflow condition for index 1. For starting index as 1. If the starting index is 0, in that case s dot top plus 1 will be the size of index, size of stack. Okay. So this overflow should always be checked before inserting or before returning the value after you insert it. Okay. First check the overflow, then only add the value. Otherwise, it will give an exception. Then comes another operation which is called pop. So pop is, we can also say it as deletion. The previous one, push, was insertion, and the second operation, which is pop, it is deletion. Okay. So what exactly it is? It is to remove the top element from the stack. It is to remove the topmost element from the stack. And for this as well, we need to have the index of that topmost element. Then only we can delete it in an efficient manner. You can anyway delete it by iterating from the starting element till the topmost element. But if you maintain this top, yeah, I missed one point. The time complexity for this push, the time complexity is big O of 1. The time complexity of this insertion is big O of 1. Why? Because we already have the value of this top. We already maintain that value of this top. So adding a specific element in an array at a fixed index is always big O of 1. That's why the insertion and deletion are efficient in this stack. Otherwise, if this s.top was not there, in that case you need to search from start, and the insertion complexity would be big O of n, where n is the size of the stack. Okay. Yeah, and we already have this top element, so this operation will also be having time complexity as big O of 1. So both push and pop operation have the constant time complexity. So the code says, and in this as well, we need to check for the underflow state. What exactly underflow state is? Check if the stack is empty or not. If the stack is empty, which is that s.top is 0 for 0 index, for 1 index. Okay, so check the value of top. If it satisfies this criteria, in that case return true. What exactly it is? It is explaining that the stack is empty. If the stack is empty, return true, and you can't delete anything from an empty stack. You can't pop element, just return. So this is the underflow check. The stack is in underflow state, which is no element is there. Otherwise, you can anyway decrease the value of top by 1. This will give us the new top. How? We have 15, 2, 9, 6. Okay, and this is top. Index is 1, 2, 3, 4. Okay, so what the operation is doing, it is decrementing the top by 1. It is decrementing the top by 1. It is removing this and pointing the top to 3. Top is equal to top minus 1. It is decrementing the value of top. So this new value will be the new top after you remove the 6 from the stack. This is what it is returning. It is returning s.top plus 1. Okay, it is returning this value 6 and decrementing the value of top. Alright, this is what the pop operation is. It will always return the topmost element which is present in this stack and decrement the value, so that next time we perform either insertion, which is push operation, or pop operation, this top will be the topmost element. Okay, again the time complexity is 1. We are only decrementing the top by 1 and returning the 6. That's it. Yeah, here is an example of these stack operations. So let's assume initially the stack was empty and you put push value 1 in that stack. Okay, so there will be only one element having value as 1. Then you again push one more element, 2. Push s, comma 2. After you push this element, it will be on top of 1. So you have this 1, now you have 2. And the new top, this is top. This is the new top. Then you perform a pop operation. This pop operation will return the topmost element, which is 2. This will return 2 and decrement the top. So the new top now becomes 1. This is the new top. Again you perform pop. Again you perform pop operation. This will return topmost element, which is 1, and the stack becomes empty. So if you try to perform pop now, it will be underflow. Okay, so it will be an underflow. So there are various, like these two operations that can be performed. Both are having time complexity as big of 1. So keep this in mind. That's why the insertions and deletions are very, very efficient when it comes to stack. Okay. So now stacks can be represented in two manner. The first is array based implementation. The second one is linked list implementation. So both, like since these arrays in Python, this is also called lists. Okay, so either you can implement a stack using a array, or you can implement a stack using a linked list. So linked list we are not discussing over here. We will discuss separately when we study about these linked lists and how they are formed, and then how they can be used to implement this data structure. Okay. So for now, we will be restricting the discussion with array-based implementations. Okay, so both of them can be either implemented in C, C++, or in Python. But specifically for Pythons, we will be using lists. So there are like various advantages and disadvantages of both these representations. So if you are going with the array-based implementation, in that case, you have to define an array. When it comes to C or CPP, an array is a fixed size memory block. It is always a fixed size block. Okay, at the time of definition, we have to define what will be the size of that array, and it is a continuous block. A fixed size continuous memory block is allocated to that variable, which is an array. Okay, so the operations are fast, but the size is fixed. It can't grow beyond the size with which we have defined that. And correspondingly, if you are implementing the stack using linked list, so size is dynamic, so there won't be any overflows. So the limitation of fixed sizes, after the stack is full, there will be an overflow. No push operations can be performed once the stack is full, but this is not the case for linked list. Okay, so overflow occurs if trying to push beyond the capacity. But specifically for Pythons, so lists in Python is a combination of both of them. So lists in Python are continuous memory, but they are dynamic. List in Python they are fixed blocks, but at the same time they have a dynamic size. How? So this is basically like, since the addition in an array, if you know the index, the addition will take big O of 1. It will be a constant time complexity operation. So I'm just giving you an overview that how these lists are implemented in Python. Okay. So again, it's a fixed block, but at the same time, it is having a dynamic size. So like whenever you define array, which is, say, let's assume ARR, define a list in Python. So what the interpreter will do is, it will allocate a fixed size, automatically allocate a fixed size. It will allocate a contiguous fixed size. And let's assume the size was, say, 100. Size was, say, 100 blocks, in which you can store 100 integers roughly. Okay, so all push operations, which is like all appends in that array till 100, all push operations till 100 will be having time complexity as big O of 1. Will be having the time complexity as big O of 1. But as soon as you try to append the 101th element, so add 101th 1th append. So this is exactly a overflow state for this list. Okay. So what the interpreter will do is, since it's like the dynamic, it is giving us an essence that the size, you have unlimited size. Okay, without worrying about like how many elements that you can push or like append in this array. So at 101th append, what it will do is it will free that initial block. It will free the initial block and allocate a larger size and copy all these elements over there in such a way that this 101th append should occur seamlessly without affecting or without letting know the user. It will free the initial block and allocate a larger one. And like this is generally like done by the interpreter on its own, and the size of the larger block won't be 101. It will be slightly like roughly it is around 15% more the previous size. If the size was like say 100, so it will be more or less around 115 blocks for the for this operation. Okay, so till 115th element you can like seamlessly add. And if you are trying to add the 116th element, say let's suppose it has allocated a size of 115, so at your 116th append it will again do the same operation. So this will, and that will be like freeing the previous block, copying all the elements to a new larger block, and then performing the 116th append. Okay, so after this 100th append, which all were in constant time, this will be big O of 100 or big O of n. So therefore the insertion or the push time complexity when it comes to list in Python is not exactly big O of 1, but the average complexity is big O of 1. It is not static. All the operation won't be big O of 1, but you can like say it that the average time complexity is big O of 1, which is constant. Okay, so generally the initial size that is allocated is like sufficient for the normal use case. Okay, but yeah, it is not always big O of 1. So this is how the interpreter ensures that the list always have the dynamic size, no overflows. All right. So now let's have a demo of how these lists are implemented in Python. So a list is used as a stack in Python. We have inbuilt utilities of these lists which we can use in such a way that it can be treated as a stack, right? So let's see. So we define directly as an empty list. Let's call it stack, right? Now we have this append function. This append function can be used to insert an element on the top of the stack, which is the push operation, right? So initially there will be empty list, and you can treat this list such that the right hand side is the point where the elements will be pushed and popped. So this will be your top, right? And the utility of append is to insert an element on the top of the stack. So initially it will be empty and the top is from the right, it is the open end. So any append operation will insert the element on the current top. Initially the top will be 0 because the list is empty. So appending an element or pushing an element on in the stack can be done like this: stack dot append and the value, let's say 10. What it will do, it will take this value and add it towards the right hand side, which is the top of the stack. So after this operation, this will be the value, right? Similarly, we have pop operation. So pop will remove the topmost element in the stack. In this case, we have 10 present in the stack. So pop will just remove it. Then if you just want to peek the topmost element and like we do not want to delete it, in that case we can use the negative indices to check what is the value of specific location, right? So in Python, the index starts with 0, so 0, 1, 2 and so on. But if we want to check the last element or the most recently appended element, or in other words we can also say it, if you want to check the topmost element in the stack, then we can use index as -1. Index as -1. So this is same as indexing the stack from right hand side, right? Okay, then we have a length operation. If we want to know what are the total number of elements present in the stack, then this length function can be used. And finally, if you want to clear the stack or the list, then directly use the clear function, right? So let's see them one by one. So initially we have defined an empty stack. Then if I print the value, it will be empty, right? Now let's append. Stack dot append 10. Then let's add one more value, 20. And 30. And now try to print it. So what will be the value? Right? First the value 10, then 20, then 30. So it will append or the push operation would be from the right hand side in this stack, right? Now let's see the pop operation. So if I perform one pop, a single pop operation, what will be the element that it will remove? And let's print it out. I'm performing a pop operation and immediately printing the value which my pop is returning. The pop operation will remove a value and return the topmost, right? The value it has removed. So at this point 30 is removed from this list or stack, right? How can we verify? If I print it, the value is 10 and 20. 30 is removed. So pop operation will always remove the topmost element from the stack, right? Okay. Similarly, what if we just need to peek the topmost element? I do not want to delete anything. So what I can do, I can just read it like this. See, 20, it will return, it has returned the last element or the most recently added element in the stack, because the stack is first in last out, right? The first element that we have added was 10, then 20, then 30, then we performed a pop operation that has removed the last element that we added, which was 30. And if we just want to see what is the topmost element, so we can see it like this, okay? And it is not removing, it has not removed the topmost element. We can verify by again printing it. See, 20 is still there, okay? And length and clear, like you can use it to see the total number of elements present in it. Oh, it is used like this. Yeah, so the stack has two elements, 10 and 20, so the length is 2. And similarly you can use clear. Okay, so this is how the stacks are implemented in Python in form of lists, right? So we can also have the class representation of stack, in which we can define a class and have some inbuilt functions push and pop. But when it comes to stack, it is not required. We can directly use list in order to have these operations. And again, these operations are constant time operations. Append is a constant time operation. Its time complexity is big O of 1. And same holds for pop. Pop operation is also a constant time operation. Why? Because internally it is maintaining the top pointer. We already know what is the length, what are the total number of elements present in the stack. So it can be removed or added at the top, right?